maybe, I don't know.
Now I'm recording. So I guess at the end of this, yeah, we can, I can post the recording at the end of this, and then that'll do it for all of you. Okay, so getting back to this, here we have an electron that's accelerated from a filament, a hot filament, through a small hole in the anode, cathode and anode, and it's accelerated across a voltage of 250 volts and flies through space for a little while. This would have to be evacuated for this to work properly, so this has to be in a tube, a vacuum tube of some kind. And then it goes into a region here with a magnetic field. So something like this, there's a magnetic field, and you should all be able to tell which direction that magnetic field is going, right? These are circles with dots in them. And so the magnetic field is coming toward us out of the paper. So in a little bit, we'll figure out what it's doing, but let's figure out first, this is going back some weeks. How fast would that electron be going? Do you know how to do that? Do you remember how to figure out how fast an electron is going when it's been accelerated through a gap of 250 volts? This is just kind of review. Does this look familiar, I hope? Does it ring a bell? Does it look like a boring problem? Katie Bear's got the right look on her face. This just looks tedious, doesn't it, Katie? Okay. So I'm hoping that you all look at that and say, yeah, I think I know how to do that. And you should be thinking in terms of energy, that the electron is accelerated and it would lose some potential energy by falling through this field. And the amount of energy, actually you can say how much energy it gains, how much kinetic energy it gains. Can you all say that? Can you just look at that and say, oh, I know the answer to that? I'm hoping so. Nod your head if you could do that. Not sure. Some of you are not sure. Well, remember, it's Q times V. It's the charge times the voltage. But you don't even have to look up the charge on the electron. You can just say the charge on the electron is 1 electron worth of charge. And then the energy is Q times V. It's electrons times volts. So it'd be 1 electron times 250 volts, or 250 electron volts. Now that's not the useful form of the energy if you're trying to calculate speed, because you need to get it in joules. So then you would have to multiply by the charge of the electron in coulombs, 1.6 times 10 to the minus 19. But you know how to do that. So that would get you the energy that it gains. How would you get how fast it's going? Can you see your way through that part of it as well? I'm hoping so. And guessing most of you remember how to do this. So we just found out how much potential energy it loses, then it gains that in kinetic energy. You just have to remember your kinetic energy formula. And that's 1/2 mv squared. So equate that to the amount of energy that it lost and solve for V. And you should be able to get an answer. Okay, you can do that one later. I'll post a solution at some point and you can check yourself on it. But now imagine that this electron travels on into the magnetic field. The first question is, how does it move? Which way does it curve? Can you look at that and see the answer? You remember how to do this? Right hand rules. Which hand do you use in this case? Should be your left hand. It's an electron, has a negative charge, so we use our left hand in general. So you point your fingers in the direction that it's moving. So that's sort of like this. And then you turn your hand so that you can curl your fingers in the direction of the field. The field's pointing up, so I have to flip my left hand over so my fingers can curl up and the thumb goes up, and everybody's got a thumb going up so that it would curve upward when it entered into this region and follow around a curved path. If we wanted to calculate the radius of that path, do you remember the formula for that? It's got a bunch of factors, four different factors that come into it. The mass, the B field, the velocity, and the charge. It's just those four factors, and that's one formula that actually you can figure out just by guessing which way each of those factors should affect it. It's m times v divided by q times b. And so if you know it's an electron, you'd look up the mass of the electron, the charge of the electron. The B field I've given you is 0.5 Tesla, and you'd have to use the first part of the problem where you calculated the velocity, and that would give you the radius. So that's talking through it. But now I'd like you to look at it again, maybe in a day or so, and see if you can do it all mathematically and get the answer. So I'll post my answer in a little while. Here's some more fun using the right hand rules. I had some fun drawing a nice cube here. I hope this has enough perspective in it that it doesn't flip for you. But this corner right here, and well, this line, let's talk about this line right here. That's supposed to be on the front side. That should look like it's out in front. And the origin of these three axes here is in the very back. I hope it looks that way to you all. So there's a B field everywhere that's going sort of up, but it's going in the Y direction as I've drawn it here. So the question is, what is the force on the various segments of this wire? And we've got current flowing coming from the Z direction, going in essentially the negative Z direction to start with. And then it goes up in the positive Y, and then the positive X, then the negative Y, and then diagonally, and so on. So let's take the sections one at a time. Can you work out the direction of the force using your hand? First of all, which hand should you be using? This is current in a wire. What do we use in that case? Should be your right hand. For current, we always use the right hand because we're doing this using the positive convention for current flow. So the arrow of current flow is telling me which way positive charges would. So start on this little section where it begins moving along the z-axis. What direction would you find the force? Point your fingers in the direction of the current. Fingers of your right hand. Curl your fingers in the direction of the field. You have to turn and curl sort of in the Y direction. And I get a force in the positive X direction. Everybody got that? Is that working? Okay. So for that little segment, it would be in the positive X direction. Let's do the next part. Here it's traveling in the Y direction, the positive Y direction. So we start with our fingers pointing in that direction. And then we turn our hands so that we can curl them in the direction of the B field. Well, this is weird. What do? We don't need to curl our fingers at all. You could turn your hand any which way. Your fingers are already going in the direction of the B field. So what does that mean? Should be a big fat zero there. There is no force because those two are parallel. If you remember, the force comes from the cross product in this case, it's the cross product of the B field, not the B field, of the current and the B field. And when those are parallel, the cross product is 0 because the sine of the angle is 0. Okay, let's do one more. How about going across the top when it's moving along here, moving in the positive x direction? What do you find there? Point your fingers in the direction of the current. Turn your hands so you can curl your fingers in the direction of the B field. You should have a thumb kind of coming out of the page. It's going to be in the positive z direction. And it's a little tricky. I would try to draw that as an arrow parallel to the z direction like this. That would be the direction of the force. Okay, I think we'll leave the rest of these for you to try to complete. And you can do that on your own time. And once again, I will post the answers. Now let's try a circuits problem. You know me well enough to know there's surely going to be a circuits problem on the test because I like circuits. You've been doing them in all kinds of forms. So here's an example circuits problem. Very similar to the ones you've been doing, although it doesn't look quite the same. It's drawn sort of vertically instead of horizontally. It's a little bit different layout, but it really amounts to virtually the same thing. Oh shoot, this is the wrong version. Where's the right version? I have it here somewhere. Oh, it's still. Drew it a little differently here, so it's the same numbers and everything. Just drew it with a little more space so that you could just print this out if you wanted to and work it. You probably want a little paper to work on anyhow. If you don't want to have to redraw all these things, then it's a little easier this way. So this is the kind of a problem that I think you should be able to work out. So here's a battery. Oh, I didn't label it on there. That's supposed to be a 12-volt battery. And then a 20 ohm resistor, a 60 ohm resistor, an 80 and a 40. And there are 3 different currents marked on here. And then down the side here I have where you're being asked to figure out what are those 3 currents and then what are a bunch of voltages. V20 just means the voltage across the 20 ohm resistor. If we were to put a meter from one side to the other, what would it read in volts? And the same thing down here, VSW is the voltage across the switch. And P20 is the power consumed in the 20 ohm resistor. How much heat is dissipated in that resistor? So there you need to calculate the power. So does this look familiar? It should certainly look familiar. Whether you know how to do it or not is perhaps a little more difficult. You might want to just think a little bit about how you would start a problem like this. Now, for the first case, we're talking about when the switch is open, and then later you do the whole thing again with the switch closed. With the switch open, is it obvious what you'd say about at least one of these things? Can you name one of the currents that you could write down right away? Look at those currents and say if the switch is open just like it's shown here. Can you name one of those currents right off the bat? You should be able to say something about I3. If that switch is open, there can't be any current flowing down here. So I3 is 0. And furthermore, you could say something about I1 and I2 when the switch is open. You see what you can conclude about I1 and I2. You should be able to see that those are the same current. You'll have current flowing around a loop up here, and it'll be the same current everywhere. Now, how would you simplify the circuit? How would you get your answer in this case? What would you do? Let's just have somebody try answering this. Shall I pick on somebody? I don't know if that's a mean thing to do. This is kind of an odd arrangement here. I will randomly pick Josh to see if you can tell us, Josh, how would you start the problem? What would you do to begin with to try to simplify it and start working it? You're going to have to turn your microphone on, Josh.
Yeah, I got it. Well, you can add the two circuits in series. Since you know I3 is 0, then you can add the 20 ohm and the 60 ohm resistors in series and find I1 and I2, which would be the same in that case.
Right. Okay. So you'd add those two. You'd see those two resistors are in series. All the current flowing through one is flowing in the next one. So those two just get added in series. You'd have 20 and 60 as 80 ohms. And then you can sort of solve the whole circuit. It's just as if you have a battery and an 80 ohm resistor. That's pretty easy to solve. What might maybe a little bit harder is to figure out voltages. Once you use that method, you're going to get the current. How would you get, for instance, V60? What's the voltage on the 60 ohm resistor in that case? Is it 12 volts?
No, so you can essentially treat it like as ratios essentially. And so you know that more of the voltage, like there'll be a greater potential difference over a greater resistance. Yeah. You know that like 60 over 80, like that ratio of the 12 volts will be over the 60 ohm resistor.
That's a fine way to do it. Another way to do it is to say once you've calculated the current, you can get the voltage across here by just taking 60 times that current. Mm-hmm. Either way is fine. You're using a sort of voltage divider approach, which is what people do when you get a little further. I haven't emphasized that particularly yet, but that's a fine way to go about it. Now, for our last question, what about the voltage on the switch? So there's no current flowing down here. It might be tempting to just say, oh, the voltage on the switch is 0. That would be the wrong answer, though.
You could find the potential difference that's in the spot on the circuit between the 20 ohm and 60 ohm resistor. And then you can just do that compared to like the 0 voltage at the switch. And that would be your potential difference.
You're trying to look at this point here?
Yes.
Yeah, trying to find that voltage. Yeah, it's actually the very same as the question we just answered. Yeah. Because we just asked what was the voltage across the 60 ohm resistor. Now, if you imagine connecting up a meter to this point in the circuit, these 2 points, and now say, well, but there's no current flowing down here. What if I move this probe from the meter from here to there? Have I changed anything?
No.
And do you see all that? Do you all see that there's no current flowing through this resistor, so there's going to be no drop. So that's the same voltage there as it is here. So I can move the probe here, and furthermore, I can move this probe from this side up to there. And now I can keep moving along these wires, and I'm right up to the very same voltage that we just calculated. So the voltage on the switch is going to be the same as the voltage on the 60 ohm resistor in that case. Okay, thank you, Josh. Let's consider now how you might go about the much harder problem of when the switch is closed. How would you do the problem then? Maybe I should redraw it here. So let's draw it with the switch closed. Now, how would you go about this problem, just in general terms? Can you describe how you would simplify things and work your way through the problem? We're not going to actually do the numbers this time. It starts getting a little hard, although I've rigged it so they aren't terribly hard. But I think I'll pick on Abby this time.